Okay, I'm live on YouTube. That's one thing. Live on YouTube is good, but it's not quite where I want to be in terms of everything else. Okay. Hello, everybody. Let's see. All right. There's me. I think there's a YouTube link over there as well. So let me start recording. Get everybody going. Nice, Mr. Bean. I see someone is a Mr. Bean fan. Excellent, excellent. Okay. So, video trivia of the day. In which 2015 video game by Bossa Studios does the player control sentient slices of bread? That's right. Very good. Is that John? You're good. All right. Okay. John, you're disqualified for the next round. So anyway, that's who was the designer? This is a tough one. Who was the designer of the 1999 game System Shock 2, also known for directing the 2007 spiritual successor to BioShock, or its spiritual successor, BioShock? That's a tough one. I think that's the studio, but it's Ken Levine was the actual designer. That's like a super, like some of these trivia questions are like super crazy specific. How many characters does the player choose from in the 1989 classic side scroller Golden Axe? How many characters can you choose from? 3. Was that a random guess, or did you know? Okay. In the insult sword fighting section of the classic adventure game The Secret of Monkey Island, what is the correct comeback to the infamous insult, "You fight like a dairy farmer"? How appropriate. You fight like a cow. That's exactly right. Very good. Okay, let's dive right in, though. So project is coming up due. So that's important. Remember that. And so today, I'm going to talk a little bit about a semi-related, but not entirely. You should have everything you need already, but in case you don't, there's always this possibility that today we might include some stuff that you might find useful. We're going to talk about basic movement for starters. Basic movement is the headliner for today. And if we have time, we'll talk a little bit about animation, because after all, animation is also generally about movement. Sometimes it's movement spatially, but sometimes it's also just movement to create the illusion of movement by animating something. But sometimes you can literally use animation as in the place of movement, or to achieve movement as well. But we'll see where we get. So there's not going to be check-ins today, but I'm just like barrel on through. Now, here's the thing. If you do, like, I'm going to try to get through things, and if you are really, really tight on time for your project, and obviously this is being recorded, so, well, anyway, I'm not going to encourage anyone. Oh, my cat is here. You can't see Callie, my cat, but she's decided to come and visit. So this is, always remember, these lectures are recorded on YouTube and available and so on. So anyway, if you need some time, if you're desperate for time on your project, well, decide wisely what you attend in person versus watch later. Obviously, some of you, because we are at 2, 4, 6, 8, not even quite 10. I'm sure there are more people watching on YouTube. 8, well, who knows? Okay. So anyway, read between the lines on that. But let's talk about basic movement, scripted and or physics compliant motion. We've already done a little bit of that in between. So what I mean by scripted versus physics compliant motion is things like sometimes you can explicitly move an object in the scene using script. And by explicitly moving, I would mean altering the transform of the object directly. So if you said transform dot position dot x equals whatever, that is a explicit change to the transform with regards to the physics engine and so on, entirely outside of the physics engine, versus using physics, which is sort of generally our preferred way of doing things. Now, obviously, if you're writing a puzzle game or you're writing some puzzle that involves, triggering animations or something, sliding blocks around or something like that, you may or may not want to do those with physics. There are certainly a lot of circumstances in certain types of games, flipping cards, whatever, that you just want to transform. You just want to manipulate the transforms directly. You don't need rigid bodies. You don't need colliders. You don't need all that sort of thing. So there is a time and a place for using, directly manipulating transforms as well. And there's going to be right ways and wrong ways, or preferred ways and recommended ways, even for that, as opposed to just directly going in and saying dot x equals, position dot x equals whatever. So we're going to talk about some of those today. And hopefully, if you haven't finished your project, this lecture may come in handy in solving some of your issues on that. Okay, so generally, when it comes to movement and position, the main building block, of course, is the vector. And sometimes we're using a vector to hold a position, but often we're using a vector as a direction and a magnitude to say, okay, we want to move in this direction some distance. Right? So generally, we're going to be using vectors. Now, in the case of 3D, we'd use a vector 3. In the case of 2D, we could use a vector 2. So in the most complete sense, we'd say vector 3 position equals new. This is how we declare and initialize a vector, right? We're getting a reference to a new vector with an x value, a y value, and a z value, okay? Or in our 2D case, we can do it for a vector 2, right? Easily enough as well. We just have an x value and a y value. Transform.position is the thing that holds the current position of a game object, of any game object in the scene. So it's specific position in the world, right? This is a world position normally, right? Additionally, we have rotation, right? It's rotation in the scene. And there's going to be also an X, a Y, and a Z rotation. In the case of a 2D game, the only rotation we're really interested in is the Z rotation, though. Right? Rotating an X and Y, or rotating around the X and the Y axes when you're in a 2D game, it has an effect, but it's not an effect that you're probably not the one you're probably interested in, right? Because if you lived in a 2D world, you would really only respect rotations around Z. They would really have like the most important thing. They're the ones that spin a 2D object in sort of the way that you expect it to. X and Y rotations when you're in 2D don't really make sense. They kind of, cause your thing to sort of collapse and do this weird affine transformation that you probably don't want to deal with. But anyway, you also have a transform.local scale, which is going to be your scaling. This is your scaling portion of your transform matrix. You may remember I talked a little bit about a transform matrix of numbers that you could use to kind of represent the current position, rotation, and scaling of an object, right? So there's the trifecta of information about where an object is in space and sort of how it's oriented and how it is scaled, right? So to move an object, it's therefore tempting to go ahead and use, manipulate the position. Say transform.position plus equals new vector 2, translate x, translate y, right? It's going to add this vector as an offset to the other, right, to its transform.position. Now, that's tempting to do it that way. Now, this frame is out of place. This is not supposed to be. What just happened? Wow. All right. Somehow I scrambled my lecture notes. All right. Well, let's go here. So this is, let's start that again. Okay. So you could potentially just change a position. You can do that sort of thing. However, you don't ever change just the X or just the Y. You have to change X and Y, or X, Y, and Z as a unit. Okay, that's one thing. A position, you have to change all, or if you add, you have to make sure that the movement that you're describing makes sense in terms of 2D or 3D. So this is the first one that you may be tempted to do, right? You may say transform dot position equals the current position plus some value. Oh, I guess I can see why I included it this way. Boy, what happened? So normally you might say, if you didn't care, you would say transform position equals the current transform position plus some offset, some increment. Now you see this is a little bit more complicated here. It's not just a number. It's not just a vector. It's actually sort of three different components. All right. The first one, when we're working with, this is just sort of a common practice, towards this sort of thing. Okay, when we're trying to manipulate a position or the position in the world, we want to offset the position according to a direction. So imagine you wanted to move it up and to the right or something like that. And then we'd also have a speed. Now you could very well have that direction be a vector that also includes speed in it. But you might want to do things like allow the player to have an accelerometer, or excuse me, a acceleration pedal, right? They have a pedal that they press and it makes them go faster or slower. Now, a pedal just has a single value. A pedal is going to have a scalar, right? Or an analog trigger. It's going to have a scalar value. It's how much do you have it pressed? So it's often good to have that separated from the direction, right? So you have one thing that controls the direction that you're pointed in, and the other one that controls your speed, right? So this is why often when we're changing position, we're manipulating how the player is moving, we have direction as one variable and speed as another variable, okay? So that's why we often, when we're moving things, we have those two separate like this. Now, the third one here, time dot delta time, and we've probably touched on this, and I'm drawing a blank today. I don't know, maybe I just haven't had enough coffee, or I teach too many different classes at this point. Now I'm trying to remember how much we got into delta time. Did we talk much about time delta time previously? You don't remember? Okay, well, in that case, I usually have mentioned that. It might come in handy. All right, it will come in handy. So the idea is that, for example, we'll jump back now. So we will jump back a few frames here. All right. All right. Somehow this got scrambled. All right. So we're jumping back. We jump back. We were back here at building blocks and vectors. All right. So we wanted to talk about that. And then, then there's this update, right? So the update function, we have encountered that, though. We've seen the update function. That gets called once per frame. So it does seem like the ideal place to do stuff in real time, the stuff that you want to have happen over and over and over again, or kind of, think of it as being the stuff you want to happen in the main loop, right? The dynamic stuff, things that happen over and over again. Like when we put our print functions in there, they got called lots and lots and lots of times. Or we wanted to have the tree, and I'm going to go ahead and pull up our Unity program where we had the tree move back and forth. We had it change we gave it a velocity and we moved left and right. We've kind of we've been doing the things the quote unquote right way. So it's sort of avoided this. This is usually, I show people the wrong way because so many people do it this other way. So you guys have just been like on top of things and we've just done it the right way. But let's look at things doing it the wrong way, or another way, I should say. So a lot of the time people think that you would just go ahead and put anything that involves real-time calculation, stuff you want to have in the main loop, you put it in your update. So it's called once per frame, right? And it is potentially time critical, like once per frame. What does that mean precisely? Like on my machine, my computer, where I have my built-in screen, my laptop's built-in screen, refreshes at 144 frames per second, right? You've all heard the term frames per second, I assume, right? When your games should be running at 60 frames per second at least, or higher, depending on, give you the least latencies and the greatest experience and so on. So these days we talk about, 60, 120, 144 frames per second, things. That's how often the computer is updating what's on the screen. Now, there's not an easy way to predict that a particular computer that you're running on, you might not know exactly how many frames per second their monitor runs at. And you probably have also experienced the case where your games don't run continuously at a constant frame rate, right? You go and suddenly that explosion happens, or you jump in the water, or, some incredibly crazy effect happens. Particles go flying everywhere, and suddenly the frame rate of your game just goes down. Maybe not by a lot, maybe by a little, maybe, dips to 50 frames per second, or it gets something ridiculous, goes all the way to 30 frames per, whatever, it goes down, right? So this update function here, it is called once per frame, but not necessarily consistently, right? An ideal case, it's going to be at the refresh rate of your display, but it might be considerably lower than that, depending on how much stuff the engine has to do. All right. So even though it seems like the best place to do things, we might need to somehow accommodate for the weird behavior. Like, imagine if I was moving at I wanted to be moving at a constant rate, where I wanted my enemy to move left and right on the screen. So at a constant rate means a constant amount per second, right? Not at a constant amount necessarily per frame if the frame rate is changing. So that's the potential problem of doing things inside of update, and why we have this a handy thing, which we'll refer to in a minute. All right, so speed, for some background, generally we're going to have the magnitude of movement is going to be your speed, your velocity, right? So to move, we're going to use this thing where we say, okay, a new position of an object. We're not using rigid bodies here. We're doing it the cheat way. We're just saying directly manipulate the position of some game object. We say, take the game object and move it in a certain direction at a certain speed. So every time update gets called, go ahead and do this. Move it by that much. But it's wrong and dangerous to do this, because update is called per frame. What happens if the frame rate slows down? Suddenly, if your frame rate drops to 30 frames per second, your player is going to actually move half the distance that they would if it was running at 60 frames per second, right? And if you programmed your game assuming that it ran at 30 frames per second, and then suddenly it was on my computer where the refresh rate of the screen was 144 frames per second, it would run more than 4 times as fast, right? Which would be terrible. And I've seen it happen. I've seen people get through all of Intro to Game Programming, even though we warn them about this, and then go into Game Dev 1 and create some kind of awesome game where suddenly, on my computer, it's totally uncontrollable and everything. It's like things move incredibly fast because they forgot this. So don't forget this. All right. This is the issue. You can't, if you're doing things in the update function, update method, don't do this. It's dangerous. If you are going to do this, you have to make some accommodation. Now, so speed, often if we wanted to move, we may expose that here. Like if this is a unit direction and we have speed, that would be, say, meters per second that we wanted to move, maybe. Or meters, if we didn't do anything, it would be meters per frame, which seems odd. So in order to accommodate or come up with a way that will accommodate this notion of doing stuff inside of update without it being inconsistent, Unity has a built-in variable called delta time. It's part of this time class, right? Time.delta time. And what time.delta time is, it is the time that has passed since the last update. The time that has passed since the last update. So if the frame rate drops to half of what it normally would be, delta time would be double what it would normally be, telling you that twice as much time has passed. So therefore, anything that you're doing that's calculating a position or calculating something that's occurring over the course of time, you need to do twice as much of, right? So it's an easy way to say, instead of saying per frame, now you can convert from per frame to per second, right? Because this will give you how much time has elapsed effectively, instantly, instantaneously per frame, right? Since the last frame. It's continuously changing, but it is per the last frame, right? So you can always use that as your modifier to convert from frames to seconds, or convert the last frame to seconds, really. Okay. So that's why we use time.delta time. So now this is a fraction of a second since the last frame. So now I know, okay, I'm going to move this much in terms of a unit vector times meters per second times some fraction of a second. So this will convert to something that will be smooth and meaningful in terms of constant speed over time, as opposed to the kind of just doing it every time the frame updates, right? So this is, if you are doing something in the update routine that is dependent on time, you always factor time.delta time into your calculation. We've sort of avoided that because we're using the physics engine, because we're using rigid bodies and so on, and setting a velocity as opposed to manipulating the position, right? If we give something a velocity to move at, in that case, the engine will automatically take care of it for us. The physics will take care of it for us because we're effectively setting a rate in meters per second. So we're bypassing this, right? So if you're working on your game and you're tempted to use transform.position, you have to take responsibility for this, right? Because you are effectively using some basically sort of an instantaneous change in velocity to move, or yeah, you may be using an instantaneous change in velocity to move something from one position to another. That's why it's a little bit wacky, a little bit dangerous. So time delta time allows you to scale the rate of change according to the elapsed time to avoid moving at different speeds at different frame rates, which you may have in your game just due to performance and the number of objects in the scene or the amount of user input or anything like that. So if you are directly changing position, make sure you do that, right? And it might not even be just transform.position. Maybe any value that you're trying to change, you're adding some increment to, or you're incrementally changing it in each update. Make sure that you add the correct increment to it. Right? There is a way to avoid that. We have a special function called fixed update, which Unity will try to call at a constant rate, no matter what the frame rate is. Right? This will generally happen at a lower frame rate, or a lower rate than the frame rate, usually 20 to 50 times per second. But it's going to happen, and Unity is going to call this function a little bit differently to kind of enforce that. This is generally considered sort of the physics update or the physics loop, right? So this one is more consistent. So if you wanted to change a position here and have a consistent delta time, you would call fixed update and put code in there. So you can put code in fixed update and avoid that a little bit, right? Here, it's okay to do that. You're still not calculating in here per second because you're just making an assumption here. But this is okay because it is at a fixed interval, right? This is one way to have things happen smoothly, but in a loop. Yes. Okay, this is, yeah. Mm-hmm. Well, if you want, let's do it with some code. Let's do an example. All right. So this will make it more clear, I think, to do an example. Now we've got the game. Let's do a whole new scene. So we'll go to scenes here and create a attempt to do it in Bolt, but I'm not gonna. I'm gonna stick with a normal scene here, and we'll call it movement. All right. So in our movement scene, we're going to have an object, and what we'll do is we'll just take an image, and I'm just going to use one of these apples and drag an apple into the scene. Okay, so there's an apple. Now, if I hit play in the scene, nothing's going to happen because the apple has no way of moving. It has no rigid body on it. It has no physics. It has no script. It's just going to sit there doing nothing. All right. So I'm going to try to move this object because I just am going to basically animate the object using a script. Think of it that way, right? This is not physics-based. This is strictly scripted motion. So I'm going to create a script, and I'm going to call it Apple Mover, an Apple Mover. This is the Apple Mover script, right? So the brute force method of moving this apple with the script, once we have it open, I could say, and I'll do it the broken way first to kind of, maybe we'll be able to prove the point. So our Apple Mover script has its default, a start and an update. So we'll say, all right, let's go to town here. Position, nope, not position. Transform, which is the thing that every object has. Oh, someone's sending me a message. Oh, I think it's someone from, okay, something else. If you are in the middle of an exam right now, obviously don't worry about checking in. But anyway, transform position. That is the position of the apple. And you see I can get it or I can set it. There's immediately a clue. If there's a get or set to it here, that means I have to use a vector 3 to talk to it. I can't just say .x equals something. It's going to be upset with me, right? See, immediately it doesn't like that. All right. So I'm going to say transform position, and I'll say new vector 2. And if I just assign that, if I just said 1, 1, for example, that's going to set the position to 1, 1. So I'll save that, and I'll come back to Unity. And right now, my apple is at -4.8 and 423, and I'm going to hit play, and it's going to move immediately to 1, 1. Okay, so I moved the apple to an explicit location. I didn't smoothly move it. I just, boom, changed its position. Right, so that's one way to move something to an exact location. That's great for teleporting things, but not really great for doing motion, smooth motion. So to do something smoother, what we would do is we would say, take the current position and add an offset to it, but we'll add some much smaller offset, right? So I'm going to call that a float and that a float. And plus equals is ambiguous now. So for plus equals, this is one of these situations where I could have said it this way. Let's do it this way. I think this would be okay. That's ambiguous too. All right. anytime you see this, if it complains about ambiguity, it's really because this position is a vector 3, right? Even though we're masquerading as a 2D game, this still is a 3D position. So to be explicit, we'll give it a vector 3. Just going to use 0 for the z value because we're not going to move it in z. All right, so we'll go ahead and say new vector 3. Now, so here what's going to happen, once per frame, I'm going to add 0.01 meters in the x direction to my position. All right, so now if I come back to Unity, I press play, it's going to look like it's moving, but you'll see if I move the mouse a lot, it's kind of moving a little slower, or even if I move the screen around, you'll see if I count this in seconds, even let's count this in seconds. So if I said 1, 2, 3, 4, 5, 6, now it's not running. So it's still, instead of being way over here where it should have been after 6 seconds, it was still over there, right? All kinds of odd things like that are happening. So what I really want to have happen is I wanted that to be smooth. I don't know if you can see that, that change not being exactly smooth. Like there, it's like speed up, slow down. If I move the mouse around, it's slow down a little bit more. It's not smooth. So instead, I would say plus this new vector times, and this is time, delta time, right? So this is going to scale this, right? This delta time, this fraction of a second, potentially. This is seconds. So we're going to say, okay, how far do I want to move per second times the number of seconds that I had to move? So now I have to come back and change this because this was some arbitrary number saying, well, I was moving 0.01 meters per frame. I don't want that to happen. I really wanted to move 1 meter per second in the world, or maybe, I don't know. Let's call it 1 meter per second. Right. So now I'm saying, all right, the position is going to be offset by this direction with a speed of 1, right? Because I don't have a separate speed here. So I'm going to say, move in this direction at that default speed according to delta time now. Scaled by delta time. Let's see. This should look smooth now, right? It's a little clunky, but if I move this around, you'll see it's better. And if I grab this and move, when I let go, I should have. I'm kind of surprised it didn't. Did I forget to save something? Nope, I saved it. Well, normally, maybe it's because of the way I'm running inside the editor. This should be at a constant rate. So maybe physics is not, delta time isn't running. But this will be much smoother now. So even if I ran this on a 60 hertz monitor versus 144 hertz monitor, it's going to be doing the right thing because I'm only going to be adding that amount per frame, right? This delta time. And now I could say, well, okay, this is my direction. And maybe I want to give the user, again, that kind of control over the speed. So I'll say times speed. Oops. And it did that because I don't have the speed. So what I'll do up here, I'm going to make this, I'm going to say vector 3 direction equals new vector 3 1 0 0, and I'm going to say float speed equals 5 meters per second, and I'm also going to make both of these public. So now I'm going to come in here and say, all right, direction and speed. Okay, so my vector will determine the direction I'm moving in, and I want this to be a unit vector. So I'll even do this. I'll say direction times normalized. So that's going to make it a unit vector. So it's going to take out any change in length here, change in magnitude, make this a pure direction. So let's watch what happens. Over here, Apple Mover should update, and we'll see there's our direction and there's our speed. So I'll hit play. It's going to move with a speed of 5 meters per second. I can slow it down, and I can even have it move in the opposite direction if I wanted. Well, let's move in that direction, right? Because I'm moving it in the negative x direction, right? Now let's set it to 0. So it's not moving at all, but now I'm going to change it from that to 1 here. So I'm going to point it in the y direction and change the speed. All right, so now I'm moving up and down smoothly. So I could give the user an accelerometer or some kind of acceleration pedal there if I wanted. And now I could even do things like say, well, let's move diagonally. And so on. Well, I'm glad you asked because I was about to show that. So if I change this, you'll notice the direction does change because now it's moving more in this negative x. This is basically the impact of this 1 is shrinking. Now, if this was just 1 and this was just 0, and let's type this in 0, 0 again, right? So here it is. I'm going to slow this down just a little bit. If I change this to 10, nothing changes. Right? That's because it's normalized. What that normalized does is it says, okay, make sure the overall length of this vector here, this direction vector, remains at 1. So it takes x squared plus y squared and divides that by, the magnitude, right? So we wind up with it making sure that square root of x squared plus y squared divided by the magnitude, right? So it winds up scaling everything so that it keeps everything with a length of 1. If we just change one without changing the other, right? So maybe this was 5 versus this being 1. Now it means, okay, for every 1 x that you move 5 y, right? It's a proportion here. Let's get it back on the screen, maybe. So this now will have an impact here because more of its speed will go into one or the other depending on that change there, right? So if I made this 10 when y is 0, it doesn't make a change. But if that's 1 and 1, it moves diagonally. If it's 10 and 1, it moves more horizontally because for every 1 y, it's moving 10 x, right? So it is normalizing it. So what's really happening is it's moving like 0.1 y and 0.9 x because it's, I mean, that's just bad math in my head, but it's changing that. It's adjusting this vector when it comes to time to do the calculation according to this normalized here, right? So normalization takes a vector and sets its length to 1. So it's a pure direction, right? So that's what's going on, right? So the vector 1, 0, 0 and the vector 10, 0, 0, they both point in the same direction. So their direction is exactly the same. It doesn't matter if it's 1, 0, 0 or 1,000,000, 0, 0. They point in exactly the same direction. It's just a matter of their magnitude. So this shortcut here, this dot normalized, we'll see that and say, oh, a million dot zero, a million zero zero should be just 100 in terms of being a unit vector, right? So it pulls out that kind of weird magnitude thing. It sets the magnitude to 1. So that's what's going on there. Yes. Yeah, because it's basically going to say, well, okay, times 10 in that direction versus, right? Without that normalization, that is going to be a direct change in that value, right? So now, now I'm basically going to have speed sort of baked into this number here, right? Woo, just shot right off the, right? So if I did this, and I'll slow it down, this is going to be the same thing as pre-multiplying it, basically, right? So if it's 1 or -1, it has a speed of 0.35. If it's -10, it has a speed of 3.5, right? So we're pre-multiplying in some magnitude or some basically speed into the direction, right? Okay. And the interesting thing about this is if you think about physics, right? If you think about physics being basically, normally we have a position, and then if we have a change in position is velocity, right? Sorry, yeah, the change in position over time is velocity. From that, we say, okay, how much did that velocity change over time? That gives us acceleration. And then we can say, well, how much did the acceleration change over time? And that gives us something called jerk, which is sort of an instantaneous change in acceleration. You know, so we have these different things where, like, over the course of time, we can change speed, we can change the speed at which we change the speed, we can change the speed at which we change the speed at which we change, and so on and so on. Those are basically all derivatives that then give you those terms that you've heard in physics, right? The velocity and acceleration and jerk, and then there's like snap, crackle, and pop. Believe it or not, yes, they're if I'm remembering correctly, there's other terms for the third, fourth, and fifth derivatives of motion. I should double check that. That'd be such a bit of disinformation if I just like said that right. Wouldn't it be great? It is good, but oh, I forgot. There's another one in between. So snap. Well, no. Okay, so the fourth derivative is also known as snap. The fifth derivative is crackle, and the sixth derivative is pop. Okay, but they're also known as potentially jounce, crackle, and pounce. Right. So this is one you want to blow the mind of your physics professor when they start talking about position, velocity, acceleration. But ask them, what about jerk, snap, crackle, and pop? You know. Right. So we can always do more derivatives, you know, instead of just doing second order, we do third, fourth, fifth, sixth, and so on. That's the joy of math, and I'll get more into that. But anyway, that's a little sidetrack. All right, we took our sidetrack for the day there. More than enough of a sidetrack. It's a great one. It really is. Everyone should know about snap, crackle, and pop in physics. If you don't, you should know about them. The physics, and this is actually an interesting one. If you were writing a game engine, and you want it to use to work smoothly, you actually do account for those things. You do actually account for higher order derivatives of motion. So that's the reason it comes to mind when I'm talking about it, is because inside game engines we do build things with that in account, because doing things on a computer, it is a discrete simulation of a real-time continuous phenomenon. Physics actually occurs in real time, but we have to calculate it in discrete time on a computer. So that's why we have to know about these things. All right. So put that in your memory bank for later. All right. So we did the simplest kind of motion here, using sort of the brute force way of saying, all right, I want to change the transform of an object according to the proper way of doing it, say, okay, let's have a direction I want to move in, a speed at which I want to move. And I'm going to recommend you do it this way because it's good practice to say, okay, let's think of the direction and the speed as two different things, right? And then accommodate for the fact that update, we really want to just change the position according to how much time has passed. That's the best way to do it, right? So if you're modifying the position, you're not using physics, do it this way. Now, that was fun. But let's come back. If I can manage to find my notes, I have a million windows open now. Wow. Did that help? Okay, well, that's good. I'm glad it helped because it is important. But I've lost my way now. Basic movement. There we go. Here we are. All right. So we don't just set a position, we add an offset to it. And generally the offset we're doing is we're saying that we have a direction, a speed, and some delta time. And since we're using plus equals, that's the same as saying equals this plus direction, speed, delta time. All right, so that's our normal method. However, an even cleaner way to do this is there is a built-in method of the transform called translate. And what a translation is a movement by an offset. So it's this same function, except explicitly telling Unity, I want to translate this object according to this amount. And the calculation is the same. It is the direction times the speed times time delta time. That gives you the offset that you want to translate. Right. So I would personally recommend that your code look like this. Transform, translate this. Okay. That's the cleanest way to do it if you are going to kind of want to slide an object around on the screen. All right. Translate the object. Your translation is a straight change in its position. And this is how much you want to translate it by during this frame update. That's just about the cleanest way to do that, if you're going that way. So in general, you want to think in terms of direction and speed, right? Motion can often take advantage of an object's orientation. So orientation has this, we have this notion of direction, the direction in which you're facing and the direction in which you're moving, right? So think about direction, right? Direction is the point in space you want to be going. Think of it that way, right? If you want to move towards this object or towards this position, it is an offset from your current position. Right. Use the built-in options whenever you can. So, other cool built-in options. When you're working with vectors, there are some built-in options called up, down, right, and left. So rather than explicitly say, I want to move 0, 1, 0 or 1, 0, 0, you can say, I want to move vector3 dot up, right? You can hard code in just directions like this, right? So we have some things set up. So we can say, move vector dot 3 up, vector 2 dot up, and it's going to do the right thing, 0, 1. Move right, move left. You can kind of just use those as shortcuts. So if you want to initialize something, they'll become even more important as we get into relative motion and rotations and things. All right. So if we were to want to move in this way, now you've noticed in our game that we had doing it the other way, the real proper way, when we went to the other scene here, our apple tree with our Snow Kid up here. Snow Kid's behavior is we set the velocity of the Snow Kid's rigid body, right? So since we explicitly set a velocity, it's just going to move in that direction. And when we wanted to change Snow Kid's direction, we actually did it by multiplying it by -1, right? We inverted it, inverted its velocity. Now, since velocity is a change in position over time, what we're sort of doing in our explicit script here, we'll jump back over to Apple Mover here, is we're basically baking in, we're kind of creating this increment, this velocity and multiplying velocity, since velocity is speed over time, and then we multiply it by how much time has passed. So this is the same thing effectively as velocity. If we wanted to change position with this, we would do the same thing that we did for Snow Kid, where we changed his velocity. One, that's changing the direction or the magnitude, having a negative is inverting our direction, right? So it calculates that same way. So we're doing that same sort of thing. All right, so I'm going to assume that you have already in your scene, you've probably moved the object around in three other different ways, using velocity for our tree moving back and forth, or Snow Kid moving back and forth. The apples were dropped and they just fell according to physics, right? So that was, their motion was entirely automatic physics. And the baskets moving back and forth, that all occurred using the actual input system, the movement of the mouse here. So we've effectively bypassed the hacky way of directly manipulating position, but you certainly can do that as well, right? So there's always at least a half a dozen ways of doing the same thing. And depending on the use, depending on what you're doing, if you just wanted to, slide a UI element around, for example, you wanted to animate something on a canvas or change the position of text on a canvas or something. For that, you obviously, you might not want to put a physics rigid body and so on canvas items. Instead, you just want to have them, kind of slide back and forth. For those, you would just manipulate the transform, that sort of thing. All right. So here we did we used random numbers to generate. Now, here's another way of using random numbers. So far we did random numbers changing the interval at which our invocation happened. Okay. You probably remember that. Hopefully we look back at enemy behavior up here. We had this drop rate, and that's the rate at which Snow Kid dropped the soldiers. And we talked about potentially changing the rate at which it changed direction. Similarly, how would you randomly change direction? We could do it by having something like this that is randomly calling the negation of the velocity, right? So if you wanted to randomly change speed, you would have some function like this one, except changing the velocity, right? I'm not going to show you exactly that because I have to leave you something to implement on your own in the game. All right. So where'd my slides go? Wow, what a day. All right. So another way to do it is, if you wanted to, what we've done by changing the rate at which invocation happens, that's the way that we kind of preferred because it's nice. We didn't have lots of calculations going on. If instead we wanted to poll, we wanted to continuously check to see, okay, do I want to make, do something at the spur of the moment sort of thing, right? We can use the random values to have, random occurrences directly. If we want to have some sort of probabilistic event that happens, like maybe in our game, maybe you want to try this. You could say, okay, I want to change direction 30% of the time, right? So what does that mean? Okay, if I have it happening in update, that would mean out of every 100 frames that occurred, the chance would be, well, actually, this would be with 0.3 would be 3 out of 10. So every, if you had 10 frames after the third frame, chances are, right, because this is a random number here, it's going to say chances are this is going to occur 1/3 of the time, right? This particular one, this is sort of an older way. I don't recommend doing this anymore as well, because if the problem is inside doing things inside of update, if you're just checking them over and over again, this is a good example of why this is potentially an issue. And let's implement it. I'll show you what the problem is. Okay, say I wanted to change the direction that the apple is moving left to right in. So maybe I want to take that function. All right. So I would say, okay, I'm going to roll some random dice and say, if that random dice is less than some threshold, change the speed. That algorithm sounds like it kind of makes sense, right? It sounds like it makes sense to say, okay, roll a die and say, if that die comes up 30% or less than 30%, change the direction. So let's see how that might work here. So we'll say, all right, if random dot value, right, that gives me my random number between 0 and 1. If I said, okay, if it's less than 0.3, then speed times equals -1. All right. So that sounds like, does anyone think that sounds like a reasonable algorithm? Say, okay, there's a 30% chance I'm going to change my speed. That kind of makes sense, right? What do you think? Right. Now you've got the intuition. You're correct in your intuition, right? How often an event occurs is going to, if I said, okay, there's only a 30% chance of this happening. However, if I check that 100 times per second, that means on 30 out of those 100, it's going to happen, right? So it's going to happen a lot. It potentially can happen a lot because I'm checking it quite often, right? Because so basically the frequency at which we call this function is going to have a real impact on the desired result. It feels right to say, okay, change 30% of the time, but we want to make sure, we have to think about when those decisions are happening. So if I just run this code as it is, you'll see that weird result. Right. So now let's go back to our other scene and movement scene. All right. So now our apple is going to sit there, and it's really kind of spastically changing back and forth. And if we get real lucky, it'll actually have a chance to move with a reasonable amount if it's real lucky. But it's certainly not really useful there, right? It's not a really useful value, right? So it's often better to have rather than check something continuously to see if an event happened, is to generate, like when we used invoke and said, okay, at some random rate that happens, and the rate is between 0.3 and 3 seconds, right? So we're only going to check, it's only going to change at some, every time it moves, every time it does change, it calculates the next time to move, right? So it happens at a much more reasonable rate, right? So if we wanted to do it this way, if we really wanted, we could bake in, right? If we really wanted that, we could bake in a time delta time and say, 0.3 times time dot delta time. So then it would say, okay, during the course of 1 second, but it's still, potentially problematic because, even though we're scaling it, because this is checking every frame, we're basically kind of trying to reduce how often this could possibly happen. And I don't really recommend that, right? So be careful about when you're using random and you're using that to like change a behavior, right? It requires some thought, which is why in the other one, when we said, okay, if I want to change randomly, do it at a much higher level and say, well, for example, the invoke, when you're determining how often that occurs, have that happen at some random rate, right? Does that follow? Does that make sense? Kind of? Okay. All right. So if anyone else tries some stuff that has weird results, just reach out to me and we'll kind of debug your random processes to see what's happening. But that is a common one that comes up when people say, "Oh, I want to have something that changes randomly." Well, think about how often the opportunity it has to change, right? Because it still can have that really, really, especially if it's like something that's a 50-50 flip of the coin. It winds up just being sort of like a really crazy jittery behavior as opposed to smoothly going back and forth, because you're giving it too much opportunity to flip that coin, right? Too many opportunities to change its mind, change its direction. I would recommend doing it a different way, to actually calculate when it should occur according to some random interval, things like that, right? That sort of thing where you want a random behavior, or you want it changing something on a random interval. It's better to calculate a random interval as opposed to dynamically checking all the time on every very, very small interval, right? It's a subtle point, but an important one. I mean, like I said, you could make the circumstance in which, if we did this, let's go ahead and try it, right? Let me undo here. If I did this and I put in time, delta time, right? So now effectively what's going to happen is this 0.3, this value here is going to become very, very, very small, right? Because this is going to be a fraction of a second times this 0.3. So this is going to be very, very small. And this is going to basically collapse. The effective nature of this is also going to collapse because it's only going to be a much smaller number that you're comparing to. So that might work a little bit better, but it's still kind of hokey, I would say, right? We're also not clamping it to the screen, so that's why it ran off the edge. Let's see, where did it wind up? There it is. So that works better. So if you want to do that, think about also clamping it to the screen. But, now it's not really being, it's happening 1/3, within a second, it's kind of scaling it down to say every second it has a 30% chance of happening, sort of, kind of. So it's a little bit, it's better, but it's still a little bit odd. All right, let's get back to here though. All right, so be careful of these sort of situations, right? Be very careful of that. You need to basically say, well, what is this, what's an appropriate value here in this direction change chance given this interval of occurrence, right? So you may need a much smaller, right? On every frame, you might want to say, oh, every frame, give it a 0.03 chance of occurring, as opposed to saying, well, it's a 1 in 3 chance. It's actually not. It should be a 1 in 100 chance, or even smaller than that. So now, if we wanted to constrain the motion of the screen, this is kind of similar to how we did our Snow Kid change in motion, except we just kind of hard-coded left and right edge to be, in this example, we hard-coded the Snow Kid to say, where are we here? Again, apple tree. So Snow Kid's behavior. Snow Kid moved back and forth, and if Snow Kid's position X became greater than 7, we clamped it to the screen. We set its position to make sure it's prior to that, and we flipped its velocity. And then the same in the negative direction. We hard-coded that, which is, again, that's kind of hard-coded numbers are never the greatest thing to use. Better to use something like, at least something that you could set via some variable, or better yet, use the functions that we talked about for getting a screen width, screen height, according to the camera. You can use that instead. But for now, we could look at it the same way, and we'll let that work either way. So this one we said, okay, if the position is less than negative or greater than the positive, you want to flip the direction. But also, we took this extra step in this particular version to say, well, okay, and then clamp the position to make sure it is actually on the screen, right? Math f.clamp is a way to say, okay, take this value and return a value that is between this lower edge and this upper edge, right? It'd be even better to say, well, maybe minus 0.001 here, to give it a little bit of leeway to make sure it's still on the frame. But this is a different way to say, okay, clamp it if you wanted to have a single if statement as opposed to have an if statement for the low condition and an if statement for the high condition. You could do it this way. But physics, yes. We want things to happen in the physics way. So we've talked about physics. Hopefully a lot of this is review, but I want to put this in the official class notes for you if you want to do this. And some of this stuff we didn't talk about. We set the velocity of the rigid body to have, say, Snow Kid moving back and forth. But the question is also, we mentioned now about rotation and scaling. What if we wanted Snow Kid to spin? So to spin, we have another type of velocity. We have angular velocity. In the case of a 2D rigid body, we have a velocity that can move in. And we also have an angular velocity that is the one type of movement that's allowed with regards to z. So angular velocity is it's spinning. Right. And we have the opportunity now, and we haven't done this yet. This will become much more a factor in our next projects, where instead of directly manipulating the velocity, setting it according to a joystick or the gas pedal or something like that, you can instead use forces to act on rigid bodies, right? When you have force fields, you have things that repel, things that collide, and so on. Instead of directly changing the velocity, it's often better to add forces or relative forces, or add torque, which is, when you want to spin something, you add a torque to it, or add a relative torque. Why is that? Well, imagine something is already moving, right? An object is already moving at a certain velocity, and you want to hit it from the side with some sort of projectile, right? You don't just want to change its velocity, its movement to some new value. You need to accommodate, you need to say, okay, how was it moving already? And with our physics engine, we can say, well, okay, let's add the new force to the rigid body, and that will maintain what it's already doing, right? It'll accommodate, it'll combine it with its motion already, right? So this is where it starts to get kind of interesting, where here we talk about, I talked about velocity, and then acceleration, and then jerk, and then snap, crackle, pop, and so on. For now, here we're just talking about, the first derivative here, right? This force is going to allow mass times acceleration. This is how we're going to accelerate objects according to, adding some force to them, right? So with rigid bodies, we're going to have these add force functions. Don't worry about them just now. We're going to use them in our projects 3 and 4, but it's something to think about. If you are done with your project and this weekend or whenever you want to start dabbling in them, create an object in your seed, add a rigid body to it, and then try affecting the object according to the other physics elements, like using forces and so on. So that's it for the basic motion and the kind of a little bit of introduction to this notion of, using forces and accelerations. All right. So let's see. How would I do that? How would I just give a quick example? So imagine if I had, in my other scene, I'm going to go to, just kind of checking time. Got really good sidetracked with Snap, Crackle, and Pop and so on. So if anyone needs time specifically to work on their project, I'm going to say, okay, now would be a reasonable time to it. We're going to do a little bit more examples. And if you want to continue to follow along, if your project's moving along well, feel free to continue to watch. Well, actually, I'll open up in general. How is everybody doing on the project? Should I do a poll? I'll do a poll. I love doing polls, right? How are the projects going? All right. That's very encouraging. Good. Are there any open issues? Right. You've seen the requirements and so on. Are there any issues you're concerned, like you don't know, or have I not gone into enough detail in terms of implementing a specific feature of the game? Right. Mm-hmm. Yep. It depends. It depends. No, it is absolutely predictable. If it's a floating point number, if it's a set of floating point numbers, it is not included. If it is an integer, all right, let me make sure that I'm remembering this correctly now as well. But yeah, it's it should tell you. It'll warn you here as well. Return a random integer number between min inclusive and max exclusive. Okay, so in the case of integers, it will not include the top number. All right, so that's probably, I think that's the opposite of what I just said, but sorry about that. I always try to remember one or the other. And so let me get that. Why am I not getting? I wanted to get the whole thing to type out there. All right. So inclusive and inclusive if it is float, right? So 0.0 to 1.0 will potentially include both 0.0 and 1.0. If it is integers, it will not include the upper end. Okay. It's a good question, and I'm glad we took the time to get out. Yes. Yeah. So definitely remember that. Me do it, like, to you to demonstrate something, or you want to ask me how I would do something? If unless you asked for something specific, I don't think there's anything I would necessarily add. I guess there's all right. There's one thing that I didn't go into detail on that you could do. So the question in the back of my head is like, okay, so one of the requirements is that you will remember here now. Let's play the game with Snow Kid up here, and as Snow Kid starts to drop these thingies here, let's see, let's scale it down again. So if I miss an item, one of the requirements is that if I miss something and it drops, it will destroy all of the other apples or dropped items on the screen. Right. So the way we did it here is, okay, so if I miss one, you see they all disappear. Right. I'll miss another one and they all disappear. Okay. Now, the way I did that in class was what I would normally regard as sort of not the most effective, fast, or not the best way to do it. But actually, the textbook, I think the Gibson, I'm forgetting my authors now again. What he does is this method. It says, okay, to destroy all of the dropped items, he just said, okay, for each game object dropped in or some value, he basically used a for each loop and used find game objects with tag. So every enemy that I dropped, every apple, every soldier that was dropped from the ship, whatever you want to refer to it as, was tagged dropped item, because the if we look here in our prefabs and we have the soldier prefab, you see it's tagged dropped item. Okay, so I'm not actually keeping track of the soldiers in a list. Oh, let me not open that one up. I'm actually just using the dropped items to that tag to figure out when to get rid of it. So the enemies that are dropped, or the enemy drops things, it instantiates them. Right, here's our kid here. Our Snow Kid is dropping these items, and the Snow Kid is not keeping track of a list of them. Okay, so there is no list of dropped items. So I kind of left that out. So an alternative way to do that, what I would regard as a much more interesting, clean way to do it, is by keeping things in a list and then destroying everything in the list. And let me show you another example that does that. The reason that it's potentially better is because this function here, where we're calling for each and this find game objects with tag, that's going through all of the game objects in the scene and checking their tags, right? So potentially this is an expensive operation, potentially. If you had hundreds of thousands of game objects in the scene, if you were able to get up to that, depending on, that could be a very expensive operation. So I recommend using lists to do it, and also just to demonstrate that you understand lists. And let's look at it in here. So here's a version of the Apple Tree game. Oh, that's a new one. Oh. That's concerning. And I might be stuck in some kind of crazy loop here. That's a good one. Go to the task manager. Ooh, I'm nervous now. I wonder if Unity changed something on us here. I don't know if you're seeing, if my screen is still visible at all. I'm probably, if the world goes to, okay, all right, it might be back now. Let's see. I'm not quite sure which one of these it is. So let's assume it's that one. And of course I chose the wrong one. All right, let's try that again. I'm not going to do the update, but I'll show the game. All right, Unity. All right. Well, something's weird with that, but at least I can play the game. So, gameplay. Here's my game screen. And here's my enemy that goes across the screen. So, the apples that are dropped have a behavior. There's an apple script. And the apples themselves, as part of the apple class, there is a list of apples. And you'll notice it is a static list of apples. And we started talking about this notion of having static variables that were unique to the whole class and they were shared across the whole class, right? So what I'm doing here by creating this static list of apples is it says there will be a list of apples that is shared across all apples in the class, right? This is a list of game objects, right? I'm using in here also the notion of the oh, no, I don't have to do that. Don't have to worry about that. Sorry, never mind. So this is getting set up once. It is statically set up. That happens once, creates this list. And then what happens is that the apple itself, it says, okay, let me start the moment I exist, the moment I come into being as an apple. I'm going to add myself to that list. All right. So this is kind of the cool thing. So it says, okay, this static is shared by all of them. And then within every apple's start routine, it says, okay, add myself to that list. And then later on it says, well, okay, if an apple drops off the bottom of the screen, it actually does a for each. But here, the for each is not of the apples that are tagged apple or tag dropped items. Instead, it basically destroys all of the apples in the list and then clears the list. Right. So this way, it doesn't have to go through and search the tags, and instead, it can use that list to get rid of all of the apples. All right. So if we don't want to do the same thing, we can do the same thing with our. Let's modify the SnowKit, if I can still open up SnowKit. I'm really worried that my Unity collab is not, Team Access is not working. That's weird. Yeah, that is weird. Team Access is working for everybody else, right? You've been updating, you've been pushing your stuff to the cloud, and that's just the first time today that I've seen that happen. Okay, all right. There's a problem. All right. Work in progress, that's no reason not to be pushing stuff into the Unity team, because that's your backup. What happens if your dog eats your computer or your computer blows up, right? You will lose your game on your computer. Don't think of Unity team and the collaborative server as just the place to submit your game, all right? You should be pushing any version you make of it up there, okay? The moment you create the initial project, it should be up there already. You should be pushing new versions every time you make a change, potentially, right? Because you don't want to lose your changes if something happens, right? So it's not just about the collaborate part. It's also a backup part, right? I get awfully upset if later on someone says, oh, my project was almost done and then my computer crashed. I'm like, well, what does that matter? All you have to do is fix the thing that you changed since the last time you submitted to the Unity team server. And someone says, well, I haven't submitted it in the last month. Like, well, why didn't you? Right? That's your backup. That is your backup. So make sure to do that. Don't only submit right before it's due or before you think it's done. Don't do that. Right? If it's any project you care about, put it, push it to the server. All right. So there, with that warning, right? Because ideally, and this is kind of, like someone who again, also as the project gets closer to the submission time, if someone says, yeah, I was really having a hard time, and I've been working on this all semester, but then the last 2 days I had a crunch, and if I see that they've been submitting, because I see the history in the server, if I see that history that yes, you've been submitting the project along the way, that is a good thing. If I don't see that constant, that you've been working on things the whole time, and you get jammed up at the last minute, I can't. How do I know that you didn't just wait till the last minute? Right. That's another good thing about the Unity team server, because it marks, basically lets you milepost your progress as well. So for next time, the moment you start working on a project, make submissions. There's no reason not to, right? Absolutely no reason not to. Unless of course it starts freaking out and blowing up on you like it's doing to me. Yes. You cannot assign more than one tag to an object. You also have to have the object can only be on one layer as well. In terms of the layers are actually more flexible. You can do things that manipulate things on multiple layers at once, but it's not so much the object itself. You really only have the opportunity to have it on a single layer and to have a single tag. Right. So they're all kind of mutually exclusive. You can only have one tag and one layer. Now, if you wanted to, if you had some reason to go beyond that, you can have components. And since you can have components, you can write a component to do anything. You could have a component that, kept track of, you could have your own pseudo layer management system. But generally, for what Unity uses, the layers and tags for having a single one is adequate. Okay, sure. Mm-hmm. Okay. Right. That's a good way to do it. Normally, I would say you could certainly do it based on it could be an index. It could be as we get into inheritance, we'll get into kind of even more elaborate ways to do that. The simplest way, kind of right now, with what you have so far, is to have a script. You can check the presence of that script. You can also see, like, does it have that component on it. So that's another potential way to look to see, oh, okay, does it have the script called enemy script or rotten apple script, or right? Or you could have a common script that they all have on them that returns a value to say which particular item it is, right? So this if it works, it's probably okay, an okay method. So you have a one common script that returns an index. Is that what you said? Right. So it's getting the index. Oh, so you're calling. Okay. So like when. Right. Right. So you're detecting the collision the same way, but then you're determining, like in here, when I had on the player script here, for example, I had this where this number of points can be set by, right? Everybody else has access to this add to score, right? So from my enemy script, I might call add to score 10, and I'd say, okay, that's whether I needed to know or not that was an enemy. My bad apple might say, okay, add to score minus points, and do that sort of thing. Mm-hmm. Okay. The only reason I would suggest having it actually pass a point value or something is because and this is more a kind of a higher level design question, right? If you're passing it in an index and you're basically baking in some information about the enemy into the player's script, right? That's right. So if I wanted to add a atom bomb or some new enemy, right, rather than just change the script of that atom bomb enemy, giving you and passing it 1,000,000 points, in your case, I would have to go in and modify the player's code to know about the atom bomb, right? So you have and this is more computer science in general question, right? In terms of trying to adopt a real object-oriented philosophy to it, is that, you know, you are causing a sort of coupling between things, in that one has to know something about the other one, you know, to kind of decide and do the right thing. So exactly. Now, if there were other things that you'd want to have happen as a result of that, that may cause you to make decisions about, you know, exposing other things or creating other methods for the player. Like if you said, oh, okay, in certain circumstances, like in mine, if I said, well, okay, certain things will destroy a basket, other things, I would have to have a add lives or something like that function that then the power-ups could call, for example, right? So instead of just destroy a basket, I might have to have an add a basket routine for my power-ups to be able to call, because the player would then know how to add a basket. It'd be important for the player to take care of that, but I'd have to expose some reasonable amount of interface to the rest of the game so that other items could invoke that behavior, right? So it's a very good question. And it's certainly, we'll get even more into that as we get into sort of more the inheritance and kind of real object-oriented stuff for the next projects. In this case, no, I didn't really build this one all the way out, but it would be, there'd be potentially a couple of ways to do it, right? I could have different scripts for each object, and they would have, you know, different number of points and different behaviors. Or another thing I could do is say, well, I have a prefab here, and this, I'll go to my prefabs. Here's my soldier prefab, which has soldier behavior in it, right? So I'll open up that soldier behavior. Normally, I add to score 1. Now, perhaps instead I want to make this, you know, this one script usable for the soldier, which I do want to catch, and the atom bomb, which I don't want to catch, or something like that. So I could say public int points or point value, and I'll give it a default of 0, perhaps. Right. So now let's pass point value in. And what I'll need to do is that in the prefab here, I'll modify that prefab for the soldier to say, the points value is 1 for that prefab. I have another type of soldier that used that same script that had a prefab where the point value is set differently. Right. So there are ways to kind of, you know, expose serialized values that are stored in the prefab, and then, you know, I could instantiate this one, and it has that value. And if I had another one, it would instantiate it and have that. You know, so I could use the same script, but change the exposed serialized variables to kind of tweak the behavior if I wanted to. And I could even say that, you know, is this something I could go one step further and say, well, this soldier, we're getting onto an advanced, you know, going down the rabbit hole here, to say, and I've done ones where, you know, maybe the, like here, is this something that causes this bad behavior? And I might say, public bool is bad to miss equals true. So by default, that's the case. And then I could say, all right, if is bad to miss, we do that. Otherwise, it's not bad to miss it, right? So I could then again, go to my prefab and say, oh, okay, it's not bad to miss this particular item, right? So I could really use this, if I wanted to, I could use this script, this class, as sort of a convenient bucket for the API or the interface between any number of potential dropped items and my player, and then just be able to kind of tune them at the Unity editor level, right? Because I can say, oh, okay, this is my one player. Now, okay, I'll do another one. I'll say, okay, I'll create another prefab here. I meant to copy it here. I duplicate. Forget which. Why can I want to duplicate? I could. Well, I could control. There we go. I just did a control drag. So this is. I could have. This will be my friendly soldier. Right. So the friendly soldier is not bad to miss. So we got to let them hit the ground, right? We got to let them get on the ground so that they do that, and their point value. If I do catch them, maybe that causes me -1 to catch a friendly soldier. So now this is the friendly soldier version. Here's the other bad soldier, enemy soldier version. And here's we get potentially into the real power of prefabs even. And I'll say, well, I'm going to make the enemy soldiers. Now let's go into their sprite renderer, and I'm going to tint those. So they're going to be darker. There's my enemy soldier that's darker. And then my friendly soldier, right? So the enemy soldier is dark. The friendly soldier is light. And now we'll get fancy here. I'm going to go back to my scene, and I'll go back to Snow Kid. And now Snow Kid knows how to drop enemy soldiers, but maybe I want to have it 50-50. Now here's a good case. So we'll say just drop prefab 2, and I'll say half the time I'm going to drop one type of enemy, the other half I'm going to drop the other, right? So now I could say here, I'll just show off, right? Try to show up here. Random dot value less than 0.5. And so if that's less than 0.5, I'm gonna drop that one. And if it's not, I'm gonna call drop prefab 2. Okay. So now what I've done is said, okay, instantiate one or the other, right? Which is gonna be, so 50% of the time it's gonna be this one. The other 50% of the time it's gonna be that one. Okay, kind of crazy. And I'll just make sure here that the second prefab is set right. So we have enemy soldier and none, and we'll come over here to these prefabs, and we'll make this friendly soldier. Put that there. So now it's going to be very confusing. And in the game, that's a bad one. There's a good one. There's a good one. There's a bad one. There's a good one. Good one. Or, oh, wait, I should cut that one. Wait, I want to catch these. I forget now. So if I miss that one, yep. See, so if I miss a dark one, oh, I get it backwards there, right? So you can accomplish quite a bit through the prefabs, and if you've kind of designed your scripts in such a way that they can be manipulated through the interface as well. There's something to be said for that, because if you're working on a team and someone else is designing levels, for example, having it be something that they can change at this level without modifying your scripts becomes a really, really good thing. And we've probably run over. Oh, we haven't run over time, amazingly, but we did use up far more time. Hopefully that was, that's kind of a, definitely an interesting, powerful thing. The Scarecrow version that I showed earlier on in the semester, that used those techniques highly, a lot. I had, the rocks that you'd catch, but they didn't hurt your score. But then there were the pitchforks. If you caught them, it did hurt your score and you lost a life. And the baskets, you could catch an extra bucket, which would give you a new life. And it was all done through that same sort of thing, kind of minimal use of extra scripts, but kind of creating, one script that would kind of, that you could kind of customize and tweak depending on what was going on, right? So it allowed you to kind of tweak the game, customize the game, kind of tune it afterwards, mod it. I could allow it for, modding, even if you didn't have access to the original script, you could mod it through the use of just what values you sort of passed it. Kind of crazy like that. Thanks for indulging me on that sidetrack there. So otherwise, if you do have any questions about the project, feel free to shoot me a direct message. There is, if you have general questions that you think could be useful to everybody, there should be a general Unity, some general questions up there. Well, I thought, do we have the general Unity questions? I know we have it in Game Dev 1 and 2. Resources, general Unity questions. There is a specific Unity questions channel. And the nice thing about that is if you post in there, sometimes other people from the class or, have the same question, or even some people who have taken the class before may chime in and help and so on. You may, who knows, find another collaborator that way. So do ask questions in the Unity questions sub-channel if you like. All right. Otherwise, I'm going to go ahead and tune out because it is now basically where we should be set. So I'll stop the stream and whatnot and reach out to me if you have any questions. All right, everybody, have a great day. Have a great evening and Wednesday, and I'll see you all on Friday. Take care.